Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Enriching Sparse Datasets with GenAI. Enriching sparse datasets presents a unique set of challenges and opportunities for data engineers, particularly when leveraging generative artificial intelligence. Sparse datasets, characterized by missing, incomplete, or imbalanced data points, often lead to inadequate model performance, skewed insights, and unreliable predictions. However, with the advent of GenAI, there is a transformative potential to enhance these datasets, thereby improving overall data quality and analysis outcomes. At the heart of this transformation are generative models like generative adversarial networks and variational autoencoders, which are designed to learn complex data distributions and generate new synthetic data points. These models can be particularly effective in data augmentation, where they can create realistic and diverse samples that fill the gaps in sparse datasets. For instance, GANs, introduced by Goodfellow et al., consist of a generator that creates data and a discriminator that evaluates its authenticity, engaging in a continuous improvement loop that results in high-quality synthetic data. To implement these models effectively, data engineers need to understand practical tools and frameworks that facilitate GenAI applications. TensorFlow and PyTorch are two predominant frameworks that support the development and deployment of GANs and VAEs. TensorFlow, with its high-level Keras API, allows for rapid prototyping and experimentation, making it ideal for iterative processes like those required in training GANs. PyTorch, known for its dynamic computation graph, offers flexibility and ease of debugging, which are crucial when adapting models to specific dataset requirements. A practical application of these tools can be seen in the healthcare sector, where patient data is often sparse due to privacy concerns and limited availability. By using GANs, synthetic patient records can be generated to train predictive models without compromising actual patient data privacy. A study by Choi et al. Demonstrated this by using GANs to generate synthetic electronic health records that maintain the statistical properties of the original dataset, thereby enhancing the training of machine learning models without risking patient confidentiality. Beyond GANs, VAEs offer another approach to enriching sparse datasets. VAEs work by encoding input data into a latent space and decoding it back to reconstruct the data, thereby learning the underlying data distribution. This capability is particularly useful for generating new data points that are not only statistically similar to the original data, but also diverse enough to cover the gaps in sparsity. VAEs have been successfully applied in scenarios like image augmentation, where they help generate new images to improve the robustness of image recognition systems. Despite the strengths of these generative models, their application in data augmentation requires careful consideration of the dataset's characteristics and the model's configuration. Hyperparameter tuning, for instance, is crucial to ensure that the synthetic data generated is both realistic and diverse. Tools like Optuna and HyperOpt can automate this tuning process, helping data engineers find the optimal model parameters efficiently. Moreover, evaluating the quality of the generated data is pivotal. Traditional metrics like RMSE and MAE might not be sufficient, as they focus on point-wise accuracy rather than the distributional similarity between real and synthetic data. Instead, metrics like the Fréchet inception distance and the inception score, originally developed for evaluating image generation models, can be adapted to assess the diversity and quality of synthetic data in various domains. One real-world example of leveraging GenAI for data augmentation is in the field of autonomous driving, where collecting sufficient real-world driving data is both expensive and time-consuming. Companies like Waymo and Tesla have utilized generative models to create simulated driving scenarios that mimic real-world conditions, thus enriching their datasets and improving the training of their autonomous systems. Additionally, the financial sector has seen applications of GenAI in fraud detection and risk assessment, where transaction data is often sparse and imbalanced. By generating synthetic transactions, financial institutions can better train their fraud detection models, increasing their ability to identify fraudulent activities without relying solely on scarce real-world examples. While the potential of GenAI in enriching sparse datasets is immense, it is essential to address the ethical and legal considerations associated with synthetic data generation. Issues of data privacy, consent, and the potential for misuse of synthetic data must be carefully managed. Adhering to guidelines, such as the General Data Protection Regulation, and developing transparent data governance frameworks are crucial steps in ensuring that the benefits of GenAI do not come at the expense of ethical standards. In conclusion, the enrichment of sparse datasets using GenAI represents a significant advancement in data engineering. By leveraging generative models like GANs and VAEs, data engineers can overcome the limitations of sparse data, leading to more accurate and reliable insights. The integration of practical tools and frameworks, coupled with a keen understanding of dataset characteristics and ethical considerations, are essential for successfully implementing these techniques. As GenAI continues to evolve, its role in data augmentation and enhancement is likely to expand, offering new opportunities for innovation and efficiency in data-driven industries. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UXL, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.